Good morning, ladies and gentlemen. I, Amrita Subramanian, welcome you all to the fourth lecture of Professor A.K. Kamal Memorial Lecture Series organized by the Department of Electronics and Communication Engineering, IIT Roorkee. On behalf of IIT Roorkee and Electronics Department, I'd like to extend a very warm welcome to our distinguished speakers, Dr. Eric Bryerton and Dr. Theodore Reck. Esteemed guests from Keysight Technologies, Mr. Vishal Gupta and Mr. Tarun Prasad, Deputy Director IIT Roorkee, Professor Uday Pratap Singh, Head of Electronics Department, Professor Nagendra Prasad Pathak, esteemed faculty, students and staff to the fourth lecture in continuation to the Professor A.K. Kamal Memorial Lecture Series, which was successfully inaugurated in 2019. This event is being conducted in the memory of Professor Aditya Kumar Kamal, who is an eminent researcher and founder head of Department of Electronics and Communication Engineering, IIT Roorkee. It's our pleasure to welcome you all to this event. We greatly look forward to listening to the viewpoints of our eminent speakers, Dr. Eric Bryerton and Dr. Theodore Reck, who will be presenting their talk on terahertz test measurement techniques. But before that, I'd like to request Professor Uday Pratap Singh, Deputy Director IIT Roorkee, to felicitate our distinguished speakers. Dr. Eric Bryerton, I request you to please come up on the stage to receive the felicitation. And Dr. Theodore Reck. And our esteemed guest from Keysight Technologies, Mr. Vishal Gupta. And Mr. Tarun Prasad. Thank you, sir. Now I request Professor Nagendra Prasad Pathak to felicitate Professor Uday Pratap Singh. Thank you, sir. We are about to commence our event by lighting the lamp of knowledge and wisdom. It's a symbolic moment that signifies the dispelling of darkness and igniting of thought and enlightenment. It's our honor to invite our distinguished speakers, Dr. Eric Bryerton and Dr. Theodore Reck, esteemed guests Mr. Vishal Gupta and Mr. Tarun Prasad, Deputy Director IIT Roorkee Professor Uday Pratap Singh, and Professor Nagendra Prasad Pathak on stage to do the honors. I invite you all to come up on the stage to light the lamp. Thank you, sir. We are privileged to have you all here. I am sure with such a distinguished assembly, we would be able to gain a new perspective from this lecture. I'd like to invite Professor Sanjeev Manas to read the biography of Professor A.K. Kamal.
Good morning, all. Distinguished guest, Dr. Eric Bryerton, Dr. Theodore Reck, Professor U.P. Singh, Professor N.P. Pathak, guest present in the audience, fellow colleagues and students. I am indeed honored to present the biography of Professor Aditya Kumar Kamal, who is the founder chairman of Department of Electronics and Communication Engineering. Professor Kamal was born in Karaina village of Muzaffarnagar, the district of UP. Just for your information, I think this place is not probably 40 kilometer, 30, 40 kilometer from Roorkee, so very close to our home, our place. And he received his bachelor's in physics from Banaras Hindu University, as well as master in science from Allahabad University. And then he also got master's degree in electronics and communication engineering from Indian Institute of Science, Bangalore. After finishing his education, he moved to England in early 1950s and worked as an engineer in Marconi Wireless and Telegraph Company, making various advancements and contributions in radar technology. He then registered for a doctorate program in prestigious Sorbonne universities in Paris, France, and also enrolled for classes in French because that required presenting thesis as well as writing thesis in French for his PhD in electrical engineering. He worked as a professor at Purdue University in West Lafayette, Indiana, and later at University of South Carolina. He sharpened his skill with industry assignments during the summers, which led with the leading organizations such as Bell Labs, Varian Associates, Center for Applied Physics at Johns Hopkins University, as well as at MIT Lincoln Labs. So after this tenure at various locations in France, England, and US, he decided to move back to India and with the vision of creating an education-related electronics and communication engineering. So he joined the University of Roorkee at that time, and he was the founding chairman of the newly created Electronics and Communication Engineering Department, and was also successful in raising capital to construct the state-of-art research facilities. And this, I believe, was way back in 1960s. And also built this 15-story communication tower that you see, which is one of the icon and proud place to see in Roorkee. After a substantial tenure at University of Roorkee, he left India again and took visiting assignments in Engineering University of École Polytechnique in Grenoble, France. And then he moved to Boston's University as professor. Professor Kamal continued to defy all odds and worked all the way through to his 90s. He had passion for life and impeccable work ethics. The last day he worked as chief engineer in Archon Corporation was at age 92. And this was a day before he passed away. So you can imagine kind of zeal he has in life. And it's really, really very, very exceptional personality that we had, fortunate of one who raised our department here. He is survived by his wife, Saroj Kamal, daughter Amita Sharma, and two sons, Pankaj and Arvind Kumar. I believe all of them live in USA. Professor Kamal was an avid reader, loved technology, and also loved tinkering with latest devices. So we welcome you all, and we look forward to the fourth lecture in A.K. Kamal Memorial Series. Thank you.
Thank you, sir. Unluckily, Mr. Pankaj Kamal, son of Professor A.K. Kamal, couldn't join us today online, but he has sent us a special video message to share his thoughts. Let's take a moment to hear from him.
Hello, and thank you for inviting me to introduce the fourth Professor A.K. Kamal Memorial Lecture Series at IIT Roorkee. I am Pankaj Kamal, his son. I'm based in Silicon Valley. It is my great honor and pleasure to welcome Dr. Bryerton and Dr. Reck as presenters of this particular edition of the lecture series. I also want to thank the Institute for honoring my father's life work in promoting education in engineering and communications. In particular, one of the key areas of his background was, in fact, in millimeter waves, microwaves, and a lot of communications in his background. And so this particular lecture series is certainly closer to the heart. So thank you once again, and wish you all the best.
Thank you, sir, for this message. Let's extend our appreciation for his time for sharing his thoughts. Thank you, sir. Now, I would like to invite Professor Uday Pratap Singh, Deputy Director, IIT Roorkee, to address the gathering.
Chief guest are these functions, Dr. Eric and Dr. Ray, head of the department, Professor Pathak, faculty colleague from the departments, dear PhD students. A very good morning to all of you. On behalf of my director, Professor K.K. Pant, and on my own behalf, I welcome you all for the fourth lecture series in memory of Professor A.K. Kamal, founder of the Department of Electronics and Communication. As told by Professor Manhas that Professor Kamal worked one day before his death. So you can just think. He was a great scientist, great professor, and we should learn from his life history that he had a passion of working. If all of you remember our past director, Professor A.K. Chaturvedi, in one of the meeting, because I was also in his team as a Dean Finance and Planning, he was discussing that the IIT Roorkee should start, lecture series, and he asked all the department that please start a lecture series on the founder head of your departments. In beginning, some of the department were very reluctant, but due to continuous efforts of Professor A.K. Chaturvedi, now I think at present all the department has started this lecture series on the name of the founder of that particular department. And today I can say this was a very good, initiative. And at least one day in the year we can hear from some eminent speakers on some emerging topics. So today we have two speakers, Dr. Eric and Dr. Reck. Fortunately, both are from the same, company, you can say, that is a Virginia Diodes Incorporation. Dr. Eric is the Vice President for Engineering and Dr. Reck is the Senior Engineers. And both the most happiness or happy things is that both are here personally to deliver this lecture. Both are giving the lecture on the test and measurement techniques in the Terahertz domain. And this was possible with the sincere effort of the present head, Professor N.P. Pathak. I am sure that the audience sitting in this hall will able to interact with both the learned speaker and they will be able to enhance their understanding of terahertz engineering. So with this remark, I thank you all and I especially thank to Professor Pathak for inviting me for this A.K. Kamal Memorial Lecture. Thank you and Jai Hind.
Thank you, sir. Moving ahead with the program, we are going to have the lecture session by Dr. Eric Bryerton. Before starting the session, I would kindly request Professor Sandeep Singh to introduce the speaker.
Good morning, all. Let me introduce Dr. Eric Bryerton. So he received his BS in electrical engineering from University of Illinois, Urbana-Champaign, and his PhD in electrical engineering from University of Colorado at Boulder. From 1999 to 2013, he was a research engineer at the National Radio Astronomy Observatory, NRAO, where he was responsible for the design, development, and construction of 30 to 950 gigahertz local oscillator system for ELMA. In detail, Atacama Large Millimeter Array. So an array consisting of 66 12-meter antennas with nearly quantum noise limited cryogenic SIS receivers located on the Atacama Plateau in northern Chile. While at the NRAO, he also developed cryogenic W-band MMIC low noise amplifiers and SIS receivers up to 1 terahertz. Before joining Virginia Diodes Inc., that in short VDI, in fall of 2013, he was the deputy assistant director of the NRAO R&D laboratory, helping to oversee the development of radio astronomy instrumentation from the radio through terahertz. Since joining VDI as a senior research engineer, Dr. Bryerton has been applying the development of highly integrated sub-millimeter and terahertz modules to many other research areas besides radio astronomy, including sub-millimeter test equipment, extender modules, CubeSat atmospheric studies, ITER, plasma diagnostics, and high data rate millimeter wave communications. So he is currently the vice president for engineering at VDI. Let's welcome him all for the talk. Thank you.
Thank you, sir. Now I'll take the opportunity to welcome Dr. Eric Bryerton. I hand over the stage to you, sir.
we have to share it only. Share it only. Also, you want to stand over there?
Stand here.
Okay, fine.
And then this is
The pointer.
advance.
That's for the program. Okay. That's for the laser. If you want to see it over there. Okay. That's for the photo.
Good morning. Thank you for the invitation, for this great honor of giving this lecture. It's very nice to hear about the history of the department, and really, this really is quite an honor. I thank you. My name is Eric Bryerton. As the introduction mentioned, I'm the VP of Engineering for Virginia Diodes. My colleague Theodore Reck will give the second part of this talk. So I'm going to be skipping slides a little bit, and then Theodore will be coming back and covering some of those areas. I believe I'll be speaking for sort of 25 or 30 minutes, and then it looks like we have a tea break, and then Theodore will be introduced and then speak for another 25 or 30 minutes. These are the topics we're going to cover. I'm just going to go right into it since we don't have that much time. And I'd like to start with starting from radio astronomy, because that is my background, as the introduction gave, and it is a lot of the background. It is the background for. It was one of the very first motivators for looking at millimeter wave, submillimeter wave, and terahertz for astronomical applications. Our company, in fact, came out of the University of Virginia. The National Radio Astronomy Observatory was looking for somebody to make Schottky diodes for millimeter wave detectors for a new millimeter wave telescope, and they looked down the street to the University of Virginia to the Semiconductor Device Lab and asked them to make a fast Schottky diode. That was back in the early 1970s, and they started a collaboration that eventually spun off and became a company called Virginia Diodes, which is where I work now. But after leaving school, I joined the National Radio Astronomy Observatory specifically to develop the receivers for ALMA. This is a 66 antenna array located in Chile. It's on a high, very dry plateau in the Andes Mountains, over 5,000 meters elevation. A wonderful site for doing radio astronomy, not for doing much else. But, yeah. Is that in my pocket? All right, is that better? Okay. Okay, so the Atacama millimeter array, it was a receiver radio astronomy instrument working in 10 different receiver bands from 50 gigahertz all the way up to close to a terahertz. They're all heterodyne mixers using superconducting mixers. And my job initially was to develop the local oscillator for those receivers. So it was develop sources, broadband sources, relatively low power, because this is an SIS mixer. They only needed 20, 30 microwatts, so not a lot of power, but it did have to be broadband and low noise. Skipping ahead, each antenna had a large cryostat, vacuum cryostat, shown here, about 1 meter in diameter, located at the focal point of a 12-meter dish. This is a vacuum cryostat that was cooled down to 4 Kelvin. And on the 4 Kelvin stage, there were superconducting mixers. And then there was a local oscillator fed to each of these receivers. And one of the primary challenges was getting enough power to these mixers at up to a terahertz, where there just really wasn't anything available until then. So at that point, there was a small company called Virginia Diodes just starting up, and they had these tunerless multipliers that worked all the way up to several hundred gigahertz, and it was just a thing to help make this instrument work, which is how I became familiar with VDI and still am to this day. So I like to motivate with some of the science that ALMA has done. I'm very proud of the work that was done on this instrument. It is both an imaging and a spectral telescope. So one of its primary motivators was to do imaging of forming disks around brand new solar systems. So this is an image, looking at nice kind of a cross section, and it has enough so that these telescopes are up to 10 kilometers apart. So you get really fine resolution, and you're able to image down to the solar system level. This is many light years away, and we're seeing these gaps forming. This is where new planets are forming, sweeping away the dust around a central star forming region. And this is looking on the right, is shown essentially the instrument working as a super sensitive spectrum analyzer. So this is looking at the atmosphere of Venus, and it's able to both have high spectral resolution and high spatial resolution. So we can look at different latitudes and look at these different chemicals. For example, this is a compound called phosphine with a transition at about 267 gigahertz, and we see a really nice transition detection shown in the mid-latitudes and not so much at the polar and equatorial regions. This was interesting because this phosphine is a chemical not expected to be seen in the atmosphere of Venus. And I just like to show that slide because it kind of shows the two different ways in which this telescope is working. ALMA has done some other fantastic things. It imaged a supermassive black hole at the center of our galaxy, as well as a neighboring galaxy. This is using ALMA in combination with other millimeter wave telescopes around the world to work as a really, really high spatial resolution instrument. So moving from there to actually doing terahertz test and measurement here on Earth. So these broadband tunerless multipliers developed with Schottky diode technology from the University of Virginia and then Virginia Diodes was, like I said, a key enabling technology for this radio astronomy instrument. And then from that, basically using the same basic technology, extended that to Schottky diode mixers, detectors, and then building those up, as I'll show, into more standardized test and measurement equipment for doing other types of measurements in the lab. And this is all based on a simple two-terminal device, a Schottky diode. So this is a SEM image of an anode of a diode here on a gallium arsenide substrate. These are then integrated onto maybe a quartz or gallium arsenide substrate with some tuning circuitry. It's assembled into a metal rectangular waveguide housing. And then in this case, this is a frequency multiplier. We have the input coming in on this rectangular waveguide here. There's the tuning circuits here, a Schottky diode, which is a nonlinear element that generates the harmonics, and then one of which, the second harmonic, goes out the output waveguide. And it essentially shows the core of how we approach generating and measuring submillimeter and terahertz. We're starting from the RF and microwave regime, where there's already a large infrastructure. There's oscillators, amplifiers that are commercially available, test and measurement equipment. And then we extend it up using a nonlinear element, the Schottky diode, either up or down, as the case may be, down to the RF and microwave, where there is, like I said, this larger infrastructure of components and equipment. The diodes were fabricated at UVA, and now that we have our own clean room just down the street at Virginia Diodes. Many different sizes and tunings of diodes. This is an array of 20 or 30 diodes, all on a single substrate for doing higher power sources. And it's a very simple, small device, low parasitics, so we can work up to 3 or 4, even 5 terahertz. So essentially, what we're doing is we're using the nonlinearity of a Schottky diode. And there's 2 different nonlinearities if you know a Schottky diode. There's, if you forward bias it, the current versus voltage characteristic. The voltage starts off, the current starts off very low until you hit, in the case of a gas Schottky diode, about 0.7 volts, and then the current kind of shoots up really high. And that nonlinearity generates harmonics of the source signal, and then you can pick off, tune for certain harmonics, and from that create a frequency multiplier. So if you put in 40 gigahertz, you can get out 80 if you double, or 120 gigahertz if you triple. And if you use that resistive nonlinearity, because it's a resistor, you can do that over a very broad bandwidth. If you bias the Schottky diode in the other direction, there's a capacitance versus voltage nonlinearity. That's a reactive nonlinearity, so you have to tune it out. So there's a very high Q to it. Because you then have to have a tuning circuit, you have to have an inductance to tune that capacitance out. It's inherently narrowband. It only works over narrowband, but it's not a resistor, so it's inherently lossless. You can have very high efficiency multipliers just over a narrower band. And we use both those characteristics. One we use for narrowband but higher power applications, and the other one we use for broadband but lower power, but where we need a full waveguide band. And that's in the case of sort of test and measurement equipment, where we want to work over a full waveguide band. And I'm going to let my colleague Theodore speak about some of the higher power applications. And I'm going to skip ahead. I apologize for the skipping through. But I'm going to skip ahead to I'm going to concentrate on the broadband, more of the general test and measurement applications. So using a resistive nonlinearity, we can, so this is looking at the frequency range 500 to 750 gigahertz as an example. So this is a full waveguide band, WM380. And just for reference, I'm showing what the 9th band of ALMA was, just to show that while ALMA was broadband, it was only about half of a full waveguide band. And we've kind of extended that out. So we have flat power. This is about -4, -3 dBm at the peak, and this is -10 dBm. So this is 100 microwatts. This is 1 milliwatt. So hundreds of microwatts, not a lot of power. It's still a lot of power for terahertz, but it's still less than a milliwatt. So this is, and it's based on this component here. This is using a cascade of these diode frequency multipliers. In some cases, 3 or 4 doublers or triplers all cascaded together, and sometimes there's an amplifier in between to boost up that power, because every time you multiply, you lose 95% of the signal coming in for these broadband applications. So we have to boost it back up. And so if you look at the back of one of these extenders, so we can come in either at below 20 gigahertz or above 40 gigahertz, skip the first multiplier, and he said there's a cascade of frequency multipliers. One difficulty in using a cascade of broadband doublers and triplers is, because we're using a Schottky diode, a nonlinear device, you're getting all the harmonics. You put in something at 20 gigahertz, you may want to get out 60 gigahertz, but you're also going to get a little bit of 40 and 80, 100, 120. You get all the harmonics of your base signal. We have tuning circuitry to tune it out, but there's only so much you can do with symmetry. So you have to put in filters afterwards, low pass, high pass filters. So as an example, this is the output frequency spectra, looking at all the different harmonics, where this is normalized to at 0 dBc is the desired harmonic. You can see when we're coming in at below 20 gigahertz, we're using actually the 54th harmonic is what we're coming out. So if you do the math, that's there's a doubler, tripler, and then another tripler. So one doubler and 3 triplers to get a factor of 54. So that's a lot of multipliers, a lot of chances for harmonics to come in. So this yellow line is at minus 20 dBc, and in the middle of the band, we do have this one harmonic. I believe that's the 53rd, is the ones that are closer in are the hardest to filter, coming up to about, this is 1% of the main tone. And that is a fundamental challenge when you're multiplying up from RF and microwave up, because you do have to deal with all the harmonics of that base signal. If you come in at the higher drive, you skip the first tripler, and of course you get a better harmonic ratio. So now looking kind of in the other direction, you have a high frequency and you want to bring it down to a lower frequency to where you can deal with it. You can use the same nonlinear element, same Schottky diode, and there's a few different ways you can do it. If you have a single diode, you can do just basic detection, where you have your RF, your millimeter wave or terahertz coming in. You're essentially rectifying it to get a DC voltage out proportional to the RF signal coming in, and that's a fairly simple device. It's a Schottky diode mounted again in a waveguide block housing. This is the waveguide flange here. This is a rectangular waveguide. We're coming in, and then there's inside of a split block, there's a Schottky diode detector mounted in, and then on this connector is a DC voltage coming out. Sensitivity of 1 or 2,000 volts per watt. It has it's a very small diode, very fast diode, so the response rate is fast. So you can have very large bandwidth of signal to detect. That's a detector, but what if you want to do a heterodyne detection? You can use the same diodes, but as a mixer, we actually use the diodes. We use 2 diodes, flip one in the other direction, use them as an anti-parallel diode. And this is a native second harmonic mixer. So it's taking a local oscillator signal, which you need if you're doing heterodyne mixing, and we're mixing the incoming RF with the second harmonic of that LO, and that difference at the intermediate frequency, the IF, is what's coming out. It's as sensitive. It's not a high harmonic mixer. It's a second harmonic mixer that's basically as sensitive as a fundamental mixer. Something like 8 or 9 or 10 dB conversion loss, and all the waveguide bands up to a terahertz or so. Again, same basic topology. The diodes are mounted in a split block metal housing with some tuning, waveguides coming in and out. And just kind of an example mixer here. You can't see it on the other side. There's going to be a waveguide for the LO, which is going to be twice as big because it's half the frequency of the RF, and then the same coax connector with your low frequency RF microwave IF coming out. This works over full D band, 100 to 180 gigahertz, double sideband mixer temperature, sort of typically 500 Kelvin noise temperature. Let's go with that. So once you have so now you can look at these as sort of having different building blocks to do more complex systems. So we have the frequency multipliers, which I talked about. You get a frequency doublers, a frequency tripler, all using Schottky diodes. And then you can take a Schottky diode mixer, which I just spoke of. You can integrate all that together because they're all integrated circuits. Put them all together in a chain inside of a single block. You can have your local oscillator signal coming in on a microwave coaxial connector. You can have your difference frequency, your IF coming back out on a coaxial connector. And in this single block, which is a fairly compact block, you have a full millimeter wave terahertz down converter with fairly excellent sensitivity. And then we have typically a single plus 5 volt or 9 volt bias for these power amplifiers in between the stages. So once you have that basic building block, once you have a down converter, that essentially forms a heart of an extender for a spectrum analyzer. So if you take that and then using the basic infrastructure of a microwave spectrum analyzer that may work to 20 gigahertz or 40 gigahertz, you can take the available local oscillator signal that's on the external mixer port of a Keysight spectrum analyzer, for example. That can connect through a cable through this into this down converter. The IF is fed back on the same cable. There's a diplexer inside this box. So now you can take all the capability that you have in that spectrum analyzer, and now that works up to say 20 gigahertz, but do the same type of measurements in different waveguide bands depending on the different boxes here. So now you can look at the spectra of a 140 gigahertz source or a 550 gigahertz source, look at the different harmonics, and look at the phase noise, for example. All the things that you do with a spectrum analyzer, a microwave spectrum analyzer, which are essentially extending it up into the millimeter wave and terahertz. With that same basic building block, you can connect it up in different ways. You can sort of sweep the LO and IF together and use it just like a regular spectrum analyzer. You can use it as a block down converter, meaning just have a single LO coming in, not sweep the LO, but then look at a really broad IF range. So and down convert an entire block of RF at once and look at it all for doing broadband communication sounding. And we can do that in all the different waveguide bands up to 1.5 terahertz. And again, very, very sensitive. So sort of compare it to kind of a classic harmonic mixer where you just have a low frequency LO and it's just just a single mixer and you're multiplying with the 36th harmonic of that. Because we're using a second harmonic mixer and then through stages multiplying up into that mixer, we get essentially the full sensitivity of a fundamental mixer all the way up to a terahertz. Noise levels on the spectrum analyzer of essentially limited by the spectrum analyzer itself, minus 150 dBm per hertz. And we can do this all the way up to 1.5 terahertz. This is looking at the conversion loss from 1.1 to 1.5 terahertz, roughly sort of 20 dB conversion loss. So still quite sensitive, even above a terahertz. Still using all the same, essentially, basic building blocks. Again, the disadvantage of working, up from RF microwave as opposed to coming kind of say down from an optical regime is you do have to deal with all those harmonics of that lower frequency. And that applies both in receiving as well as transmission, meaning that you do get some mixing off these other unwanted products. So we have to be very careful to do filtering at every stage. And then we do characterize this in our extenders, looking at the conversion from these unwanted harmonics. Try and limit that to 10 or even 20 dB below the intended the intended mixing product. But it is a very difficult process. This has been used for many different applications. This is from a few years ago doing regulatory testing of the first 5G handset for automotive emissions applications, where again, it's sort of doing kind of regulatory emissions testing of a 94 gigahertz radar, but looking at the emissions all the way up to 330 gigahertz to make sure those are below the standards. Using this same spectrum analyzer extender capability, also using the noise source drive and noise figure meter application in the spectrum analyzer, we can do noise figure measurements up in the sub-millimeter wave as well. This is a noise source based on a Schottky diode as well. And then we have using a down converter, very similar to what I showed for the spectrum analyzer extenders, the device under test in the middle. You can do a full noise figure measurement characterization of some device under test. And for example, this is a 100 to 130 gigahertz low noise amp that we have developed for some other radiometer applications. So it's doing a characterization of the noise figure and gain of that amplifier. And using Schottky diodes, we have noise sources up to 220 gigahertz, up to 330 gigahertz. You see that this noise source has much higher ENR. That's based on actually an amplifier that we developed. Yeah, so now I want to move on to so there's a couple different ways to go up from a microwave signal up to millimeter wave or terahertz. You can just straight multiply it up through a cascade of frequency multipliers, kind of what I've shown here, or you can mix it up. So instead of, I was talking about a mixing down from terahertz to microwave, but it works, it's reciprocal, it works the same way in the other direction. You can have the IF coming into it. We have the same high frequency LO, and then we're mixing up that IF signal up into the millimeter wave. The disadvantage of just straight multiplying, the advantage is you don't need a local oscillator drive. The output can be high power, but you're essentially losing all that phase information of the input signal, because this is a highly nonlinear operation, of course. And you're losing essentially all the amplitude information except just a basic kind of on-off, a 1-0. Because again, this is very nonlinear. For this mixing, this is, even though using a nonlinear element, the mixing up itself is essentially a linear process. It's preserving the linearity of your input signal. So you can have a full broadband signal with lots of modulation, lots of information encoded in it, and all that is preserved as it's translated, as it's mixed up to a higher frequency. So we take advantage of that in our up and down converters. So using again, we're using this building block of frequency multipliers. It's shown as a single one, but for higher frequencies, this can be a whole cascade of multipliers. We'll need some signal generator at microwave frequencies, some synthesizer. And then we also have that Schottky diode mixer, which is doing the up conversion or down conversion. In this case, this is shown as a down converter, but it works both ways. Here's it shown as an up converter. You do get these are inherently double sideband mixers, so you get that IF, you get that signal at both, copied at both the lower sideband of the LO and in the upper sideband. In many cases, you will want to filter out one of those sidebands. Luckily, this is in waveguide, so it's fairly easy to make a very high filter with very high cutoffs, very sharp cutoffs. This is what we do. For example, this is a waveguide iris filter. You can have many poles to make it have a very sharp response. So these are different filters, just a few gigahertz wide. This is shown in E-band, for example. But you can do that up to several hundred gigahertz. So we filter out, one of the sidebands, and then you'll often want to boost up that signal. To preserve linearity, you're somewhat limited in the power coming out of this mixer. You don't want to saturate this diode. You don't want to saturate the mixer. So the power coming out here is maybe about a microwatt. So you'll want to boost that up with a power amplifier if you can. So we have some broadband and narrowband amplifiers. This is an example of a broadband power amplifier. This is based on an indium phosphide HBT transistor, MMIC, something like 18 to 20 dBm of saturated output power. And this is an example. This is a key site demonstration using our up converters and down converters up to D band, along with one of the AWR arbitrary waveform generator, a very fast oscilloscope. So you can do very broadband, few gigahertz wide transmission and detection of comm signals for a 6G testbed. This is 16 QAM at 144 gigahertz. This is one example. This is a year or two old. I've seen some better examples more recently. And kind of the last sort of test and measurement application I want to speak of is sort of combining everything that we've talked about so far. So both the multipliers for a signal generator extender and then the mixer down converters for spectrum analyzer extender. If you move all that, put all that together, you now have a complete network analyzer extender. And kind of what do we use network analyzers for? Is to measure the complex scattering parameters of some device under test. And you want to do that because you want to get all the information to fully characterize the device in both directions, amplitude and phase. You need all that in order if you want to transfer to the time domain, for example. And then with a network analyzer, you have the ability to do very advanced calibrations. We can calibrate all the way up to the device under test. So inside network analyzer extender, we have all those building blocks I spoke of. We have a cascade of frequency multipliers. We have, in this case, two different down converters. We have one to down convert the signal to sample the signal going out. And then we have another one that samples a signal through a coupler coming back in. And that gives us our full, we have this on both sides of the device under test. That gives the full 2 port S parameters, both in transmission and reflection. Because we know the signal that's going out and we know the signal that's coming back in. That's mixed down, and then both of those are sent back to the baseband network analyzer at a lower frequency. Again, in the local oscillator, we're also have frequency multipliers split to the different mixers. So again, we're using all these different building blocks of the diode multipliers and mixers to do this entire assembly. There. So this is an example shown on a P-site PNAX. Yeah, so this essentially, again, the whole idea is that we want to do all the same types of measurements that we could do using RF microwave test equipment, to do all that at millimeter wave and terahertz. In this case, we want to do full calibrated 2 port S parameters. And we have those extenders from all the way from 26 to 40 gigahertz all the way up to 1.5 terahertz. And this seems a little funny at first that we have extenders. I mean, to me, this seems like a very low frequency to have a frequency extender, 26 to 40 gigahertz. Because again, you could have the network analyzer itself over coax measure at 40 gigahertz. But there's a kind of an interesting use case for why you would not want to do that. And that's in antenna test chambers, where you might have a very long, say 5 or 10 meter distance between your base unit, your network analyzer, and your actual device under test. So 5 meters of coaxial cable at 40 gigahertz is quite lost to you. You're losing a lot of sensitivity. So there actually is an advantage to having your down converter, right at the antenna, and then sending that down converter signal back at, a few hundred megahertz on this coaxial cable where the loss is quite a bit less. Yeah, basically the basic theory of VNA network analyzers and calibration. You have you're sampling both your device, your wave going out, your wave coming back in. You're doing this on both sides. You're measuring the ratios, and that ratios are your scattering parameters and would allow you to fully characterize your device. As part of the you need to be able to calibrate out all these other effects of your what you're doing to all your couplers and attenuators and mixers and amplifiers. You calibrate, and waveguides need to calibrate all that out. So you're actually measuring at this reference plane here, and it's a very complex set of error terms inside the network analyzer. So you have to do a full sort of several different ways to do kind of a full calibration of measuring test devices to take out those effects on your measurements. And if you've done that, there's a couple different methods. There's a sets of standards. There's a SOLT, which is a short open load and through, or there's a TRL, which is a through or a flux and a line. And we do both of those, but we're doing them in rectangular waveguide. And although we do both methods kind of everywhere, we tend to use the TRL method up to about 330 gigahertz. And the reason is, for this line standard, that line is a quarter wave of waveguide. And the way you make a quarter wave of waveguide is you have a very thin kind of wafer-like shim with a rectangular hole cut through it. And that's your 90 degrees of waveguide. But of course, as the frequency goes up, the wavelength gets much smaller. So that shim becomes incredibly small, incredibly fragile. We do have shims, quarter wave shims, and we do sometimes do TRL calibrations up to 1.1 terahertz. It's not something that you would want to have kind of in a regular laboratory environment where it's being used a lot, because it just won't last very long. So we use a short open load through calibration, and a nice thing we can take advantage of there is, while you can't have a open in waveguide, right? If you just have a waveguide open, it's not an open circuit, it's just an antenna that radiates out fairly well. You don't get a whole lot of reflection. But instead, is we take a short in waveguide is easy to do. You just put a piece of metal at the end of the waveguide, and now it's a short. And now if you then delay that short, if you have 90 degrees of waveguide and then the short, that kind of moves around the Smith chart, now you're back to an open. So now you have an open circuit. So an open circuit is easy to do in that case. And that's how we do that. So here, this is our quote open circuit. It's just we're just milling down a quarter wave in this very small waveguide. And then at the bottom, of course, is just metal. So that's your short. This is just kind of shows the whole thing there. So inside here are kind of all these building blocks that I referred to before. There's two of those down converters, one for the reference and one for the received. So I know there's, and then there's a set of multipliers for the RF signal that comes out. This is a D-band 6.5 extender shown for an example. Dynamic range is essentially limited by the network analyzer itself, 120 dB at 10 hertz bandwidth with something like 13 to 15 dBm test port power. And something else kind of I wanted to show is, this is an extender at 750 to 1100 gigahertz. And there's some challenges. There's many challenges. The one challenge is, as you multiply up, you're also multiplying up the phase noise by 20 log n, of course, of your signal. So if you want to do this type of measurement, you need to have very, very clean synthesizers, because the your phase noise is continually getting worse as you multiply it up. So you need to start with something very good so that when you down convert, you're still in this narrow detection bandwidth. Otherwise, everything's just get washed out and you're losing signal. And that's what we would see if we would use one of these extenders, with a synthesizer that wasn't so good. And luckily, kind of in the new generation of Keysight synthesizers that are in their PNAs, have much lower phase noise, so our dynamic range goes up considerably, up to over 100 dB typical, even up to a terahertz. This is an example, VNA testing. It's kind of a very high frequency waveguide filter, sort of at the limits now of what you can do with metal machining. This was developed as part of a space project where we needed very sharp filters at 690 gigahertz. The filter was simulated in HFSS and then measured using a network analyzer extender. And then we found out there was some disagreement between that and the simulation, found out it was due to a very small gap, which we could then model in our simulation tool. Extenders can be used on probe stations, very convenient for that. Where you don't want a long waveguide run to the probe, so you want to be able to have small extenders that can go connect right to the probe. Recently, this has been probes have been developed to do full DC to 220 gigahertz sweeps. That's shown here. So I'm going to skip kind of fast. I want to get to this example of doing antenna characterization. Again, showing the extender right at the device under test on the antenna stage. And I want to move on to Theodore here shortly. We can do kind of variations of this. We can add in a second source to the extender. The reason you want to do that is if you're measuring power amplifiers, for example, and you want to look at the nonlinearity, you want to have two tones coming in. So we can do that as well. We're improving the power of those by using broader power combined amplifiers. And kind of one of the most recent things we've done for test and measurement is combine both the VNA extender with an up converter, so that we can do full characterization of broadband modulated signals with a PNA. And that sample of that's shown here. Here's the extender, and then here's the up converter, the mixer up converter module. So this is broadband characterization. This is our first customer in Stuttgart, Germany, using that system, which they actually helped us develop and test. And then I kind of wanted to move back to space to talk about some of our work on CubeSat radiometers for doing weather monitoring and other things. And I want to end my portion of the talk, and I'm going to let Theodore take over, talk about this, probably preceded by some of the higher power sources. But it seems like now is a good time to do that. So again, this was quite an honor. I'll do this. Thank you again for the opportunity, and thanks for your attention. I'll pass on, please.
Thank you, sir. Thank you, Dr. Eric Bryerton, for sharing your experience in the terahertz detection and signal generation. And we really thank you for showing us endless possibilities in this terahertz frequency range using the Schottky diodes and frequency multipliers. Thank you, sir. Now I cordially invite our esteemed guests and audience for a delightful high tea. Thank you, everyone. Enjoy your high tea and have a great time. After that, there is a session by Dr. Theodore Reck. 15 minutes break it is. Please take the tea and come. Thank you. Welcome back to the session. We are about to begin the lecture by Dr. Theodore Reck. Before that, I request Professor Priyansha Kaurav to introduce the speaker.
I hope everybody is now freshened up with the tea and ready for another great speaker. So let me welcome Dr. Theodore Reck. He has received his Bachelor of Science in Electrical Engineering from the University of Texas at Austin in 2000 and PhD from University of Virginia in 2010. From 2011 to 2018, he was a member of the technical staff at NASA JPL, where he developed novel components and systems for future spaceborne remote sensing instruments. During his time with NASA, Dr. Reck developed high-frequency radar transceiver arrays, high-power multimeter sources, novel packaging techniques, and cryogenic MMIC-based receiver systems. In 2018, Dr. Reck became a senior engineer at Virginia Diodes Inc. His current research interests include high-frequency mixer and multiplier design, power combining techniques, and high-frequency metrology. He's a senior member of the IEEE and the author of over 25 journal and 50 conferences publications. Let us welcome Dr. Reck.
Thank you, ma'am. It's my pleasure to seize this moment to welcome Dr. Theodore Reck. Sir, the dais is all yours. Welcome.
It's the same. I'm just going to start. All right. Well, thanks again for having us here. It's a great honor. I was a postdoc at NASA under Gautam Chattopadhyay, who has been a great mentor for me over the years. So I'm very happy to be visiting his homeland and being able to share some of what he's taught me. My talk will be a little bit more specific. I work on more of the component side of VDI, so I'll be talking about our high power sources, specifically around the amplifier work we've been doing, as well as, then I'll jump to what Eric mentioned, our radiometer work, which is where we are, thank you, where we're developing highly sensitive instruments for remote sensing, in space, and So let's start with this sources summary. This we didn't include the terahertz gap slide in our talk, but this kind of highlights what the problem is with terahertz. Is it gets harder and harder to generate power as you move higher in frequency. This is a combination of different amplifier sources in yellow, multipliers in blue, and then there are fundamental oscillators, quantum cascade lasers, but there you're moving down in frequency and you get less and less power as you approach a terahertz. And then there are fundamental oscillators like resonant tunnel diodes that do operate up to a terahertz, but again, their power is very low. Now, we, of course, specialize with Schottky diodes, so we're focused on multiplier sources. So some of our latest generation of multiplier sources are these larger blue dots. So I'd say 300 gigahertz, we're getting 100 milliwatts. but these are all powered by the amplifiers that we've recently developed. And that's been the case for decades now with Terahertz technology. As new amplifier technology comes, then we can add multipliers after those amplifiers and then bring up the available power. Let's see, there we go. And so the critical technology that we've been using at VDI is indium phosphide HBT amplifiers. So these we have developed in, well, these MMICs have been developed at Teledyne Scientific. And this shows the on-wafer powers of several of their broadband chips. And then to the right, you can see these are the packaged powers that you get once they're in a waveguide housing. And so, we're adding the packaging component to these amplifiers, and then we're able to integrate them into systems. As well, not shown over here, are these narrowband high power amps. And these are very interesting in terms of either generating higher frequency LO sources or amplifying communication systems, particularly around G-band. These have been very interesting, particularly this amplifier, because it has higher saturation point and you can get more uncompressed signal out of it. So we've been very successful at packaging these. We're losing very little power, usually less than a dB, going from the on-wafer measurements into the package, and then it's available to integrate into your system. But of course, everybody wants more power. If you're getting 200 milliwatts, wouldn't it be nice to have 4? Particularly if you're doing comms, you need to keep pushing that saturation point higher if you want longer range communication links. So the solution for now is power combining, because right now the chips are kind of combined as much as possible on chip. And so we have been developing a lot of waveguide power combiners. The key technology is this Magic T combiner we've developed. It's full waveguide band, so that avoids having to design a waveguide component for multiple ones for each waveguide band. And so you can see excellent return loss, of course 3 dB split from the input port to the output port, and then good isolation below 15 dB. And that's important when you're combining to keep the different amplifiers from talking to each other, either to avoid standing waves or even worse, oscillations once they're power combined. Of course, then we take that and 4-way combine it, because if you can, you just want more power. And we've been able to create a waveguide component of a 4-way combiner, essentially 3 Magic T's, and it comes in from the bottom and then out the input from in the center. And I'll show a real picture of it in a second. But you can see these are all back-to-back measurements. So we take one 4-way combiner, attach it to another one, and then measure the loss through it to get a sense of the waveguide losses of the total component. And so these are twice what you would get, twice the loss you would expect in a power combined module. W band, we're at half a dB, 6.5, again, just creeping up. WR 5.1 from 140 to 220 is still just 1 dB, but you can see at 4.3, we're starting to get into trouble because the waveguide losses are starting to affect us. So you can see this is tracking the loss of a waveguide pretty well. So, but it's still useful, up to above 200 gigahertz in particular. Once we have that 4-way combiner as well as a discrete 2-way combiner, then we can combine our amplifier modules in different combinations. So that 130 amp I showed in that first slide, we two-way combined it to get 26 dBm, then you four-way to get another 2.5 dB. You know, it's not quite 3 dB, nothing's perfect. And then four-way, or excuse me, so this was four-way, and then this was eight-way. And there's multiple ways you can do these configurations. We kind of have this Lego approach right now where we're still sort of sussing out the best approach to packaging this many chips in one system. But you can either go for a four-way, each one of these could be an individual amp, but we've also made a package this size that is two-way combined, and so then you can go eight-way. But we've also developed four-way modules as well. So yeah, here are our powers. We've all the way out to 250 gigahertz. We're getting, you know, up to 25 dBm for that eight-way combined module. So as an example of where these have been used is for radio astronomy. We developed a 2 terahertz LO system for radio astronomy. And so here we just needed, the spec was 80 microwatts from 1.8 terahertz to 2.1 terahertz. And so, but the key driver of this system was this four-way combined amplifier at 150 to 175. And you can see where, you know, we had to build multiple of these systems. So these are two different four-way amplifiers we developed, getting 500 milliwatts, and this one's closer to 600. And then you can put that, a varactor multiplier after that. And so now we're getting over 100 milliwatts from 300 to 350. And then moving on up, we have another doubler at 650 gigahertz, and then finally our power at 1.8 to 2.1. And these suckouts here are the atmosphere absorbing the power. And so if you're not familiar with it, the SOFIA instrument was a airborne telescope. The idea, similar to ALMA, is to get high up in the atmosphere, away from all those atmospheric absorption lines that you saw in our measurement. And unfortunately, it was decommissioned, was very expensive to operate, and and so eventually it was put out of commission. But it was quite a piece of technology, and we really enjoyed contributing to it. Yeah, so here's our final system. It's hard to see a little bit, but yeah, here's the final system integrated into the cartridge that was going to fly on the telescope. It's actually 2 pixels, which they then optically coupled to their HEB detectors. There's our big amplifier and our multiplier chain, and it was driven by one of those integrated amplifier multiplier modules that Eric talked about earlier. As another example of a high power system, this is sort of like a heroic effort. We took 2 four-way combined amplifiers shown here, those big blocks. There's actually 2 of them. This one's obscured by the fans. Drove it with another amplifier multiplier module, split the power there, drove those 4-way amplifiers, and then into it, a 2-way combined 256 gigahertz doubler. And we were able to achieve over 250 milliwatts across that customer's frequency band. This was the power from the 8-way combined module. So very useful powers, not only for radio astronomy. I think this could eventually find use in comm systems. Okay, so because of the way the talk kind of happened, I'm going to jump forward to the radiometers. Oh, I'm going the wrong way. So you saw all this good stuff. So another aspect of our business has been contributing to these space and CubeSat missions in particular. This is something that Eric led as a tropics mission in collaboration with Lincoln Labs, MIT, and it's a direct detection radiometer around 180 gigahertz. So we essentially it has a here's the block diagram. It starts with 2 low noise amplifiers, splits, and then goes through 3 different channels that are again amplified and then direct detected with one of our Schottky diodes. And then that video signal is then amplified and then used to detect the system. It integrated one of the noise diodes as well as a calibration metric, which could be toggled on and off to stabilize the receiver over time. Here's the whole system integrated into it. Here's the radiometer that we developed. There was a 90 to 118 gigahertz radiometer, and both of them were coupled into this reflector here. Very compact because it fits into a CubeSat, which are all very small. Essentially, the whole satellite was about 3 times this large. Yeah, there's a better picture of it. So yeah, to talk a little bit about CubeSats, it's kind of the perfect space-borne mission for VDI in that it's a sort of a low-cost platform to fly instruments, and it allows new technologies to be deployed and tested. But it's a real challenge to get low-power, compact systems, compact instruments into them. So that's where we come in with our high levels of integration. Tropics was designed as a constellation, so you would build up multiple of these so that you can get high temporal resolution of a storm. So you'd have multiple satellites flying over the hurricane or whatever you're studying, so that you could get cross sections of it over time. So yeah, so 12 radiometer channels, and it all needed to fit within 1 U of that CubeSat. So here is some initial imagery of a hurricane, and then recently 4 satellites, launched in May. So. And so, as I mentioned before, one of the components that enables these are packaged low noise amplifiers. So we've been able to work with various companies to get these low noise amplifiers packaged into our systems, but we also integrate them into the radiometers as well. But we sell them as standalone components for comm systems. An earlier CubeSat instrument that we flew before my time, actually, so I didn't fly it, Eric flew it, was IceCube in collaboration with Goddard, NASA Goddard. This one was a, I'm blanking on the band. Oh yeah, it was 830 gigahertz, way up there. So imagine getting a receiver at 800 gigahertz into a 1U CubeSat where you probably only had 10 to 20 watts of power to operate off of, and that would need to supply the synthesizer as well as the amplifier multiplier chain. So this instrument was addressing a gap in the measurement of clouds, and the 183 gigahertz or 830 gigahertz band allows you to see or study the development of ice in the clouds, which was a first. So there it is, integrated into that 1U platform. Again, this is our contribution, and then there's the whole IF backend, and power supply and control units. And this was deployed from the ISS back in 2017. And then they were able to study the radiance of that band, 883, excuse me, across the planet during that first launch. As well, we've developed polarimetric or polarimeters that essentially are one of our integrated mixer amplifier chains, but it includes ortho mode transducer on the front end of it. So you're actually measuring two polarizations at once, which again is valuable in terms of studying the science and studying I know for the ice clouds, the polarization of the light emitted from the ice is important to the science that they're developing. So yeah, we've just been funded to develop this instrument that will be flown on CubeSats. We've already developed much of this technology already on an earlier SBIR, but it was just selected for funding, and it's scheduled to launch in 2027. And another system that I was directly involved in was SOLVE. And so this was to look at water measurements on the moon. And so we wanted to look at abundances of H2O, HO, and deuterated water as well, HDO. And this tells you a lot about not only how much water there is, but also the source of it. And so again, they're targeting a CubeSat, but they would actually put it on the moon and look at the sun and use an occultation measurement, they call it. So they would look at the amount of power absorbed by the water in the atmosphere of the moon to study the abundance of it. And so there were two channels. One was a 530 gigahertz channel and a 2.5 terahertz channel. And this was a real challenge for us, but because we're looking for low power instruments. Luckily, because we're staring at the sun, you don't need a very sensitive mixer. So they required 50,000 Kelvin noise temperature on that channel. But the power requirement was very challenging, 7 watts for that receiver. And so to do that, well, let me first talk about the 530 channel. This is very similar to our integrated mixer amplifier blocks. It's designed to operate at a single LO and have to have a very high IF bandwidth. And so in this situation, in this measurement, we were just looking at the noise temperature across the band, but we actually operated at 530 gigahertz, and then you look at the two side bands. There's a strong absorption line at for regular water at 557 gigahertz, and then the deuterated water is, I believe it's around 110 or 510 or 520 gigahertz. And so you use a high IF to capture both of those lines simultaneously and then down convert them. But then the 2.5 channel was a real challenge, and I won't go through the details here, but there hadn't been a lot of work done up there. We had done a little bit of work with a third harmonic mixer, but it was just not sensitive enough for this system. And so we decided on a fourth harmonic mixer which would allow us to take advantage of the anti-parallel diode pair, which actually gives better conversion loss than, say, a third harmonic mixer, because you're able to use that energy that's trapped in the anti-parallel pair. So here are some simulations of that mixer, probably getting into the weeds here a little bit, but I'm super proud of this. This was a lot of fun. But you can see in simulation, we were showing about 24 dB conversion loss with 2 milliwatts of LO power. Of course, that at 2.5 terahertz. And being fourth harmonic, that means we're able to pump it at a low frequency of 625 gigahertz. Yeah, there's the assembly, very challenging assembly. We split it into two, so we're actually integrating the mixer on the diodes onto the tuning circuit. So this whole thing is a gallium arsenide circuit with our integrated Schottky diodes there, and then our RF probe here. And then the LO comes in from the left on this big chip. This is actually a quartz substrate, and then the IF comes out that way. So here's some measurements of that mixer. So conversion loss are these green dots. That was around 23 dB, pretty close to simulation, honestly. Of course, this is double sideband, and those simulations were single sideband. So we were still close, but 2 dB off. And then here's our noise temperature. Came in a bit higher than we had hoped for, but this is actually system noise, so it includes the contribution of the IF noise temperature. Now, to get that into a CubeSat, we needed to develop a whole LO system to drive it that was low power. And so here is our package mixer with an integrated diagonal horn. And then behind it, to drive it, we have essentially a WR6.5 IAMC, but a narrow band, because we included one of our Teledyne amplifiers here to drive it, which allows us very efficiently to get 150 milliwatts to drive 2 varactor multipliers. And then that gives us enough power. Let's see, do I have power? Yes. So that gives us over 3 milliwatts to drive the mixer. And then just, this is the power of that amplifier at this point. So there's the whole system operating at 2.5 terahertz. We had to look at how it behaved over temperature. You could see that we're just over 65,000 Kelvin, which is, or actually we could optimally pump it here at 60,000 if it was a little bit cooler at 20 C. So, so that ends rather abruptly, but that gives you a taste of sort of both sides of VDI. Our core business, of course, is in test and measurement, but we're able to take a lot of that technology and apply it to some of these really exciting space applications. And that technology development then comes back around and feeds our test and measurement business. For instance, we're taking a lot of the power combined amplifiers that we've been developing for these custom systems and putting them into the VNA system. So now that you can do better, have more power available on your VNA measurements to allow you to do more load pole type systems, or explore saturation characteristics of amplifiers directly. So thank you very much for your attention. So.
Component they were power combining to generate high power.
Yes.
They were not, but waveform they were combining. Is there any way to report what's happening? Size is becoming very large.
Yeah.
Power divider, power combining, losses, power combining goes.
Yeah. Well, that's a very good point. Our technical capability is more on the waveguide packaging approach, and we're actually more interested in lower levels of combining at first, so 2-way, 4-way, but it's kind of gotten out of hand. People are starting to ask for more power, and now we're starting to look at higher levels of power combining, and I think we will have to take a look at doing maybe radial type a combiner using microstrip or something like that to reduce the size, because you're right, they're getting very large. Yeah.
Consistency of phase matching for this four-way power combiner over the band, that will become an issue.
Yeah.
So what kind of power command efficiency we are getting here?
I'm seeing, I usually think of it in terms of combining losses, but we're always under 1 dB. And like at 130 and 150, it's closer to half a dB of combining efficiency, which I believe would be 90% or so, if I'm doing the math right. So.
What motivates me to go for this kind of source? Why not quantum cascade laser type for the same amount of power?
Well, with the quantum cascade laser, you need cryogenic cooling, which is difficult to deploy in a commercial environment. But if that's not an obstacle to you, particularly at higher frequencies, the quantum cascade lasers are the way. If you need milliwatts or tens of milliwatts even at 2 or 3 terahertz. But quantum cascade lasers kind of run out of gas as you go down. And so photonic mixing maybe would be the way to get to lower frequencies. But the issues there are phase noise can be a problem in terms of, particularly for comms applications. You need good phase noise, and getting those two lasers locked tightly to get good phase noise with your mixed signal is a challenge. I know people are starting to make progress there, but that's historically been the challenge.
One more, this powers what you are showing, they are almost saturated powers.
Those are saturated powers, yes, yes.
For the COM type of application, where we want to employ the vector modulations.
Yes.
So much 2, 3, 4 dB back off I have to go.
Yeah, it's closer to 6 for P1 dB on these. These amplifiers have kind of a soft saturation characteristic.
Soft saturated.
Yeah, so 6 dB, worst case.
If I go 6 dB back off, how much power I'll get and how I'll get the ranges? Coverage for communication. And what kind of application you are looking for there, where we are not able to get so much of power?
Well, for our applications, many of our customers are looking just for power, whether it be like for Sophia to drive a very high frequency varactor system, or another application people are using it is dynamic nuclear resonance, or no, the acronym is DMP, where it's chemists studying chemicals, where they're actually hitting it with terahertz and looking at how it rings to study the chemical properties. So they just need a high power source. So.
Okay, last question. Can you just imagine one killer application of terahertz?
The killer app question.
I'm trying to looking at least one killer application you can tell. Without terahertz, this work cannot be done.
Geometry. Historically, that has been the killer app. I mean, it's not a big moneymaker, but there's no other way to study the atmosphere in the same way.
So dynamic range of radiometer 2 to 3 dB maximum. How you are able to show the profile of the hurricane? I don't understand. Either you keep on integrating for a large time.
Yes, exactly.
Because radiometer hardly we get 3 dB dynamic maximum.
Sure.
Yes, yes.
Do you well, the integration time, well, the dynamic range of the radiometer is a few dB. But the way they study it is by integrating, but we're not even integrating that long typically.
But typically it's like sort of 10 milliseconds
Right, yeah.
per spot. And then it's kind of spinning and then calibrating off the cold sky, and then passing over Yeah, it's basically 10 milliseconds per pixel, something like, and that gives you like a half Kelvin, 0.5 Kelvin of any delta T. So that's your that's your temperature resolution.
10 milliseconds.
Right.
That which is
Well, it's something like 2 gigahertz of bandwidth, yeah, per channel.
dynamic scenario, 10 milliseconds. You will get. Hurricane is dynamically better.
Right. Right. So that, yeah, that's the idea of a constellation is you want it, because right now, using, one of the the larger weather satellites, you're coming over a hurricane every 6 hours, right? So you're only getting update on its state every 6 hours, which is okay, but it's not enough because it's moving, it changes very fast, right? So if you have a constellation of smaller satellites that are cheaper, you can come up, hit the same spot another satellite comes over every 30 minutes, say. So now you get every 30 minutes, you get a new.
My source at this frequency, are you embed diode or something else?
For these we're using they're just Schottky diodes. They're biased close to breakdown in reverse breakdown. Yeah, so that gives you your noise. That's your noise mechanism.
Broadband?
It's broadband. So essentially it's a whole waveguide band. It's producing noise over that range. It's not, the ENR is not super high. It's, at 180 gigahertz, it's maybe 10 dB, 9 or 10 dB of ENR. So it's not a lot of noise, but for doing sort of something like this, it's enough to do calibration.
With 10 dB in or how accurate you are able to measure an
How accurately can we measure noise figure of an LNA? I don't know the exact answer to that. Honestly, do you know?
Yeah, I mean, I recently kind of looked at how accurately we characterize our noise diodes, and it's hard because it's a power measurement. So it depends a lot on the accuracy of all your instruments, and you can cascade the uncertainties, and it's close to a dB.
I'll take that question.
Okay.
So it will be dependent on a few factors, like we do the uncertainty calculation using noise figure analyzer, and it will be in a down conversion mode that we'll be doing the calculation for, wherein the prime factors to contribute to the uncertainty of the noise figure measurement will be coming from the ENR uncertainty. So how good is the ENR specs of the noise source? That is number one, which is the prime factor. Second one is on the uncertainty of the instrument, that is the noise figure analyzer that you're using. And third one is the DUT input VSWR. So these three factors will be contributing to the noise figure uncertainty measurement, and we need to do the calculation. So there's no straight figure for that. So these three will be the prime factors to contribute to the noise figure uncertainty.
that the P1 dB is closer to.
So are we planning to have a higher power sources or amplifier in VDI for further application in communication? Because there we need long ranges.
We are working on it, but it depends a lot on MMIC technology and how it evolves. And this is already kind of as good as we can get right now. As I imagine it's coming, particularly as GaN moves up in frequency, that's coming, I hope. But the reason we haven't looked at it so much is GaN is typically more narrowband, and at lower frequencies, there's chips that work fine for us. Below, GaN is kind of operating now at like 90 to 100 gigahertz. So.
Somewhere I seen your power combining, your waveguide height has come low. Why you did that? Magic T?
Yeah, it was Magic
Magic
Key.
Key, your waveguide height has come down.
Yes, yes.
For impedance matching or what?
Yeah, it's impedance matching to that fourth port, which goes through the microstrip circuit. So.
Thank you.
So you can, if you have further queries, you can email to us. We will have it communicated through. They will be there.
Thank you, Dr. Theodore Reck. We express our gratitude for enlightening, guiding, and inspiring young minds on the prospects of Terahertz technologies. And we really thank you. Your talk has been instrumental for advancing our understanding in the practical context of Terahertz measurements, including high power sources. Also, we could gain some insights into the radio meters for remote sensing applications. And we were also excited to hear from you the water measurement in moon. Thank you, sir. Thank you so much for your talk. Now, I would like to invite Professor Nagendra Prasad Pathak on the stage to present the shawl and memento for the distinguished speakers. Dr. Eric Bryerton. Sir, please come up on the stage to receive the shawl. And Dr. Theodore Reck. Sir, please come up on the stage. Thank you, sir. Now I'd like to invite Professor Amalendu Patnaik to present the memento to the esteemed guest from Keysight Technologies, Mr. Vishal Gupta. And Mr. Tarun Prasad. Thank you, sir. Now I request Professor Nagendra Prasad Pathak to deliver the vote of thanks.
So, good afternoon to all of you. This is final step, of this A.K. Kamal Memorial Lecture. That as a head of Electronics and Communication Engineering Department, this is my duty to express my sincere thanks to all those who traveled from, say, United States and accepted our visit to come here, invitation to come and visit IIT Roorkee and deliver talk, and all those who are involved in organizing this function. So I'm reading that special vote of thanks. Before that, I would like to mention few things. Like this year we are entering into the 60th year of the department. Department is going to become 60-year-old department. So this is a special moment for us. And you know, in 1964, this department, this was established by Professor A.K. Kamal. And at that time, it was very difficult to convince senators and university board to start a new department when there were very few talkers about the electronics area. Because electrical engineering was very mature and very established area. But it was Professor Kamal who was able to convince most of the senators and policy makers at that time. At that time, it was an university. He was able to convince them about the importance of this stream, especially electronics and communication stream. And this is a reality because I was told by one of our alumni who was here in somewhere 1970s, early 70s. So he said that Professor Kamal was a super vice chancellor. He was vice chancellor of vice chancellors because whatever he wanted, he was able to do that. And Kamal Tower is one of the example of his efforts. You can see a 15-story tower that is one of the symbol of our existence in this institute. So this department is also known on the name of Professor Kamal and Kamal Tower. So my say few words more I would like to mention here about the department. This department has progressed a lot. So when it was started as a small department, then there were 4 research streams. Initially, there was microelectronics, microwave, and communication, and one more was the control systems. In 1980s, 81 or 82, we hosted one more stream, that is the stream of computer science and engineering. And with the addition of computer science and engineering stream, our number of groups became 5. In 2013, Indian Institute of Technology Management and Board, they decided to separate computer science and engineering as a separate department. So it was carved out from electronics and communication engineering. So in between, it was electronics and computer engineering department, and now computer science and engineering is a separate department since almost 10 years. And the old department is again renamed as electronics and communication. So we have not only progressed in terms of technology, in terms of our faculty strength, our alumni, our students. In the stream, we also hosted a new branch. And everybody knowing that computer science is a full-fledged branch and one of the most preferred area of our students. We are sharing the same building so far, computer science and electronics. So I am reading the vote of thanks because this is also very, very important. A special thanks to Dr. Eric, Vice President Engineering of Virginia Diode, and Dr. Theodore Reck, who is Senior Engineer at Virginia Diode. Apart from that, we would also like to thank Professor U.P. Singh, our fellow colleagues and our students, that they have attended the lectures with full zeal, and the lecture was delivered by Dr. Eric and Dr. Theodore. I also express my sincere thanks to all my faculty colleagues for being here today. I would like to thank all the students, volunteers, and our department staff who came forward to make this event a grand success. Let me also express my thanks to the support team from across our institute, Dean of Alumni Affairs for their support, Institute Computer Center for setting up the international call, auditorium staff for providing the hall, and making the arrangements and media cell for giving the coverage. We would also like to thank IEEE student branch volunteers that they basically arranged this entire event. So they were from the concept, they were involved. And next half of the talk will be in the department where some demonstration work, etc. that is scheduled. So thank you all those volunteers who were involved in and they were putting their efforts day and night for the success of this event. They need a special thank. A special thank also goes to Professor Priyansa Kaurav because she has joined in this department just 6 months back, and she contributed a lot. And you know that this entire thing was managed by Professor Kaurav. So thank you for your efforts. At all, thanks to the staff who are involved in this Kalam blog and ICC staff who were directly involved for broadcasting of this event. Thank you everybody. Thank you a lot.
Thank you, sir. Presently, our department is expanding its horizons in research, with the Terahertz specialization being the latest addition. However, it's crucial to recall our origins and reflect on the remarkable journey that we have undertaken. This lecture series provides us with the opportunity to remember and thank Professor A.K. Kamal, who laid the foundation of electronics and communication engineering at IIT Roorkee. I am sure we all will be looking forward to the next lecture series in 2024. With this, we have come to the second part of this session, which will be conducted in the Terahertz and Communication Lab of EC Department from 2:30. I extend a warm invitation to our guests for lunch at NC Nigam Guest House. Thank you everyone for being such a wonderful audience. Have a great day ahead. Thank you.